Hi, I'm Pravir and I'm a postdoc with Barak at Weizmann. And today I'm going to talk about, or I will update you about the progress of this pruning algorithm. This is designed to find pulsars in short wave binary systems. So I think previous speakers have already motivated us that why we need to detect pulsars in short period binaries. I will skip this, but you can see that how the complexity increases if we want to detect tighter orbit binaries, as we have the parameter space increases, and if we want to detect orbits with orbital period less than 2 hours, then we have to probe all these acceleration, jerk, and higher derivative terms. So we need to consider these orbital motion effects in our searches, and so these will be the only equations. So, so we have to correct for this Doppler effect, and this phase relation equation will have extra terms. Right. So, what are the limitations of the current algorithms? Pulsars are faint, so obviously we need hours of coherent integration to detect something, but the parameter space is large. We have, of course, we have the dispersion measure first, then we have the period, and then we have the other orbital parameters. So the complexity grows as a function of time, and we are doing a blind enumeration over all the options, and depending on the configuration setup we are using for our search, the complexity grows as t to the power k, where k would be 6 for a jerk search. So the total number of trials or the options would easily be in this range, 10 to the power 25, 35, depending on the search configuration, if you are doing a all-sky search, things like that. And then the problem becomes very computing intensive, and then we use GPUs for those kind of searches. So usually to avoid this growing complexity, we assume constant acceleration, and we only search up to the second order terms, but then we limit our integration time to some fraction of the orbital period, and thus we lose sensitivity. So we would ideally want to integrate longer times to be more sensitive, but then we have to deal with the complexity. So we need to find an algorithm which can deal with this growing complexity and should preserve the sensitivity. So we solve this by this pruning algorithm. So our workflow consists of 2 steps. The first step is a FFA-based search up to some desired segment length, and then in the next stage we then turn on the pruning algorithm and then prune options which are not feasible. So why FFA? Because FFA, we want to be coherent. So FFA coherently sums all harmonics, and it's more sensitive than FFT-based searches. And FFA is also more sensitive for narrow pulses and longer period signals. So this is a comparison of FFA versus FFT sensitivity, and this is a theoretical FFA sensitivity promise, which is to be coherent for all duty cycles. And so this portion of the parameter space, which is now missed by the FFT-based searches. So we build our stack on FFA. So just to give a brief intro about FFA, FFA is fast folding algorithm. We divide our data into small segments. So let's say if we have 2 segments, we coherently search each segment and form folded profiles for all the options that are possible, and then we combine these 2 segments to form folded profiles for the combined segment by using the folded profiles that we already have in memory. So we don't need to compute another set of folded profiles. We just use the folded profiles in the previous iteration. So that's how we can get the folded profiles for the entire segment length in an optimal way. So 2 key things here. The trial folded profiles are always kept in memory, and our FFA implementation is different from the existing one. So this is a bottom-up approach. So, and we have the recipe to extend it to higher order polynomial searches. So that can be easily extendable to jerk, snap, etc. So this is a plot of the FFA sensitivity for an acceleration search example. I have injected some pulsars, and the interesting plot is this one, the last one. So this is the recovered significance as a function of duty cycle, and the different curves are with different tolerance levels. So the tolerance level, I say that okay, I'm okay to lose some sensitivity, but so I will increase my step size by this factor, and that will improve my runtime. But I'm acceptable for losing some sensitivity. So this shows that our algorithm is converging, and we are sensitive for almost all the duty cycle range. These sensitivity curves can be further improved because there are many errors which can be minimized, and so that's also a work in progress. Right. So now we have an FFA which we can use for jerk or acceleration search, and we have arrived at a stage where we have all the folded profiles for all the options that we want, but it doesn't reduce the complexity. It just finds a way to get it in an optimal way. So that there pruning comes into play. So pruning, we use partial information to make a decision. So we keep adding data, but at the same time, since the signal significance has improved, we remove things which are not statistically significant. So we use a signal to noise threshold, which the survival probability is exponential in nature. So the overall complexity, instead of growing as a t to the power k, we'll also have the elimination term, which is exponential in nature, and which helps to decrease this complexity curve by this amount. So so the t to the power k complexity will increase exponentially, but at the same time we are pruning things, and so at some stage we will reach, the algorithm will converge, and the complexity will not increase in that amount. We will reach a convergence. Okay. So to further visualize the pruning process, let's say we stop the FFA at some level and we have some n segments left with. These n segments are already coherently searched, and we have all of the folded profiles in memory. We now add the one segment to the next segment, and by doing this our segment length will increase, and so the parameter resolution space will increase, and so we have more number of options that can be possible in the same grid. So we can visualize it as the existing options branching into more options. So that's how the complexity will increase. But at the same time, since assuming that there is signal in our data, so the signal significance will also increase if we have more data. So we will use some threshold, and we will only keep options which are above certain threshold in our this tree, and we will only propagate those branches. And in the end, we will reduce the complexity by a huge amount. So the key thing here is to determine the correct threshold at each stage. Should we be more conservative? Should we be more aggressive? Because we don't want to lose the candidate in any of the stage. So what should be the signal to noise threshold at each pruning iteration? And that was the key question that we needed to solve. So here I visualize different thresholding schemes in the top plot, which is signal to noise ratio as versus the segment iteration. And then I see how the complexity, which is the false alarm options, how it grows, and I also see how the cumulative success probability grows. So the cumulative success probability is the probability that in the end we retrieve the true signal. This is the H1 and this is the H1 hypothesis. So here I compare different schemes. Some of the schemes are the bound scheme is a scheme where I assume that when I add two things, the signal to noise square will add in a linear fashion. So I assume that the signal to noise is distributed equally in all the segments, and so this is in this signal to noise space. This would be square root n in this curve, and so I can see that while the complexity decreases with segment iteration, but the success probability is quite less. So this is not what we ideally want. We can then say that, okay, let's fix the complexity. We choose the thresholds in such a way that we fix the complexity at each stage, and we do get a higher success probability, but then we have to deal with this huge volume of complexity, which we do not want. So what should be the ideal solution? So what we did is we solved it on a grid. We went through each path. So this is the threshold signal to noise, and this is the segment iteration. What the answer that we want is what should be the ideal path in this different nodes, which will maximize the probability of finding pulsar, but at the same time it will minimize the computational complexity. So this can be solved using a Viterbi-like approach, and we can get this blue curve, which is the most optimal solution. And we can see that the blue curve has a high success probability than the bound scheme here, and it also has less complexity than this orange one. So, but we would also like to ask this question that, okay, can we guarantee some success probability in the end, and give me the best path, give me the path which will minimize the complexity. So that can also be done using this approach, and we can say that, okay, I want a path which gives me a probability of 0.3 in the end, and the path that minimizes it. Yes, yeah, that's all. So these are the ongoing work which are happening. So we are putting up many safeguard mechanism for RF fine bright candidates, and eventually we will put up it in a package and see how it works in the real data. Okay. Any questions? So complexity is important because yes, so all of this is just for one option, but let's say if we have 100 segments left with, and then we have like thousands of options. Options means like different combinations of period, acceleration, jerk, and if you are doing a circular orbit search, then we would have a fourth derivative, and I'm not even going to Keplerian searches. So if we are not very aggressive, if we are very conservative, then the tree volume or the number of options that we are keeping will be huge. And since we are keeping all the folded profiles in memory, we will need like a huge amount of memory to do all this. So we want the path which is the optimal in the sense that minimizes the complexity as much as it can. But it also gives some finite amount of success probability in the end, that it's guaranteed that there is a 0.3 probability that in the end we end up with the pulsar. And then what we can do is, you can see here that in this blue curve, all the success probability comes from this first 10 iterations. The other iterations are not contributing to it. So in a sense, these are the only independent ones. So what we can do is we can start another pruning instance at iteration 11 with the seed. So seed as segment 11, and then we can start another one at segment 21. So we can start multiple pruning processes in the same data, and it's like a binomial trial where you have a success probability of 0.3 for one trial, but you do like n trials, and then the probability of at least one success will improve to 0.9 or something. So right now we are using these parameterization, which is acceleration, jerk, and these kind of things. But I think we've already discussed that because eventually the basis becomes non-orthogonal, and then we end up with Chebyshev polynomials. Yeah.
Mm-hmm.
Yes, so there are some issues which needs to be solved for a Keplerian search, but as long as circular orbit search is concerned, I think we have solved most of the issues. I agree with you. Yeah, so if we have like 100,000 combinations of parameters that if we want to keep, then, and we are keeping let's say 64 bins, and so floats values, it's huge.
All right. We have no more time for questions. Thank you very much.